a weight that pulls the rocket down, and then there is a thrust from the engines that propels the rocket upwards. And this thrust is due to the exhaust gas that comes out from the engines. And I'll try to explain this for a very simple example. It's actually not very different from a balloon. So imagine that you have a balloon in your hand and you pinch it closed. You have here the gas in the middle of the balloon, and it's in an equilibrium state. And there is pressure on the walls of the balloon, of course. And once you actually let go of the balloon, the gas will come out in this very little hole and basically propel the gas in this direction. And the balloon, by reaction of the forces, will actually be propelled in the other direction. And this is very, very simplified how a rocket engine works. And I'll show you a bit more detailed image of this. So this is a schematic of how an actual rocket engine looks like. There are different types of engines. There are liquid, hybrid, and solid engines. This is a liquid one. And basically what you see here is that you have two different tanks in the engine. You have the fuel here in this tank, and you have also an oxidizer in this tank. And what happens is that you basically have these pumps that pump these oxidizer and fuel into this combustion chamber. And when these oxidizer and fuel mix, you ignite it so that you create a reaction, like an expansion of the gases. And this combustion chamber is quite small, but it creates like a huge pressure inside it. And once this gas wants to escape, it pushes through the throat of this is what we call the nozzle of the rocket engine. And it pushes through here and basically expels all of the gas that is created through the nozzle of the rocket. And here you see, the equation of how much thrust you can generate with this rocket. And I'll explain a bit better how this equation works, or how this, why does expelling the gas actually make the rocket go forward or upwards? So imagine that we have, again, a very simplified model of a rocket. Imagine that you are now at time 0, and the rocket has a certain velocity, it has a certain mass, and also the fuel that is in the back of the rocket has a certain delta mass. It has a certain smaller amount of mass than the rocket. And then you go to a time where t equals delta t, so a short, very, very short time after after you start firing the engines. And what happens is that basically the gas that you saw in the last picture, it is actually expelled through the back of the rocket. And the important thing here is that when this gas is expelled, there is a conservation of momentum, which means that the gas has some velocity that goes in one direction, and the rocket will go then in the other direction with a certain delta V. And this is basically summarized in one of the most important equations of rocket science, which is called the rocket equation. And here you can see that it says that the delta V equals to the exhaust velocity of the gases, which is this velocity that the gases exit with, times the natural logarithm of the mass, which was the mass that the rocket started with, divided by the final mass of the rocket. And this is very important because it means that what governs how much velocity you can get is actually the amount, the speed of which you can expel the gases, and also the amount of fuel in the tanks, right? So if you have very much fuel in your rocket compared to the total mass of the rocket, you will be able to go much, much faster than if you have a very low amount of fuel. So, one thing that is very important to know about rockets is that, at least today, it's actually, well, it's never been done, it's impossible to actually launch something into orbit with just one rocket. Right, and what does that mean? It means that if you have a rocket that you saw on the image before with just one tank, it will never reach orbit. It will just basically go up and then down again. So there were some smart people that came up with this concept of rocket staging. And what that means is that you see here, again, the SpaceX Falcon 9 rocket. And you see here that this part is actually the first stage of the rocket, and this part is the second stage. And then you have here on the top, you have the payload, which is actually what is going to be launched into orbit. And the way it works is that when you start the rocket, it is only the first stage that ignites first. And once all of the propellant from the first stage is actually gone, it's expelled, what happens is that you drop this stage because you don't need this mass anymore. And if you have less mass, you need less force to actually go to orbit. And then once this stage is separated, it actually falls down into the ocean, or in the case of SpaceX, it actually lands again and it can be reused. And then once this is gone, you have kind of a mini rocket on top that is then ignited, and then it continues to launch your satellite into orbit. And the way it looks like is a bit like this. This is just a drawing, but this is what the separation looks like. So when you are at a certain altitude at a certain time in your launch sequence, you actually drop off this stage and you start firing these other rocket engines that are from the second stage. And usually rockets have between 2 and 3 stages depending on the rocket. And one interesting thing to know is that a rocket is basically, it's almost always 90% of fuel. So what it means is that you need basically all of your mass that you have inside the rocket is for the fuel. Only 6% is for the actual structure of the rocket. So if you would empty it of all the fuel, it would only weigh 1/10 of what it would be with the fuel. And only 4% of the rocket is actually the payload, the satellite, for example, that is launched into space. And the reason is that you need a lot of power to be able to launch into space. And in this case, this is actually the Saturn V rocket that took the astronauts to the moon. And in this case, you see here that the astronauts is only a very, very, very small, tiny part of the rocket. So you can imagine how they felt when they sat on top of this. I think it was around 2 million kilograms of explosives, and they sit there on the top waiting for the launch. So I can imagine it might have been quite terrifying to be there. So I'm going to talk about some interesting concepts about maneuvering in space, because it's not really as easy as on Earth. Like on Earth, we know if I go this way, I'm going to end up there, right? In space, it's a bit different, because there are the equations that govern the orbits and basically the forces are a bit different. So there are some counterintuitive properties when you have to maneuver in space. So I told you in the beginning that there are some different kinds of orbits, right? So you have the low Earth orbit, which is up to 1,000 kilometers. Then you have the medium Earth orbit, which is up to 10,000 kilometers, and then you have the geostationary orbits, which are, well, 35,000 something kilometers. And basically, the geostationary orbit is one that actually where you rotate at the same speed of the Earth. So it means that satellites in this orbit can actually point always to the same place on the Earth. The ones that are in the lower orbits, they actually go faster, so that they will go around Earth many more times per day than the geostationary orbits. And this is something that also can be a bit counterintuitive. You would maybe think that if you have a higher orbit, you would go faster around, but that's not true. Basically, the lower orbit you have, the faster you will go around Earth. And the reason is that the gravity is much stronger the closer to Earth that you are. So basically, you need a higher velocity to counteract the gravity to not fall back down on Earth. So if you are further away from Earth in the geostationary orbit, you actually need less velocity. So, for example, in the low Earth orbit, you need around 7.8 kilometers per second as your speed. But if you are in the geostationary orbit, you only need around 3 kilometers per second to go around the Earth. So, I will talk a bit about how you get from one orbit to the other, because usually when you launch a satellite, you actually launch it always into a low Earth orbit, and then you have to basically maneuver to get into the higher orbits. And the way it works is that you see this green orbit. This is a low Earth orbit, and it has a certain distance to the Earth. And at some point in this orbit, you actually, with your satellites, it works a bit like the rocket engines. You actually expel gas backwards, which makes you get a certain change in velocity, so that your velocity is higher. And then you basically, once your velocity is higher, your orbit will change. So it will go something like this, come up to a higher orbit, but then it will go back down again. So if you would only do one burn here, you would actually stay in this elliptical orbit and always go around like this. So what you have to do to basically go to a higher orbit is that you also have to do a burn up here. So once you have done a burn here and you come up all the way here, you have to do another delta V. So you have to put more propellant to propel you forward, and you go around to your new orbit. And the thing that is counterintuitive that I told you about in the last slide is that actually, even though that you add velocity here and here, you will actually go slower in the larger orbit than you were in the lower orbit. So another interesting concept, if we don't want to stay in the Earth orbit, but if we actually want to go further out in space, you need a lot of velocity to go outside of our solar system, for example. And to go further, like for example the Voyager spacecrafts that are now in interstellar space, we use something that is called a planetary swing by, or gravity assist, if you will call it. And the way it works is that you start here on Earth with an orbit around the Earth, and then you actually have a trajectory where you pass by all of the big planets on the way, and these planets basically give you an extra push, extra velocity to go further out in the solar system. And actually what happens is that when you approach this planet, there are two things that are going to happen. First, the planet is going to change your direction because of the gravity of the planet. So the gravity will pull you closer to the planet and actually change the direction that you're moving. And while you're passing the planet, since both the planet and the satellite will have forces acting on each other, actually part of the momentum of the planet will be transferred to the satellite. Now, if you pass by, for example, Jupiter with a satellite that weighs a couple of 100 kilograms, on Jupiter this will not be measurable, because Jupiter will probably have a very, very small force since it's so massive. But for the satellite that weighs only a couple of 100 kilograms, it will have a huge effect on the velocity that you gain. So basically, we use this planetary swing by to gain velocity. So every time it passes one of these big planets, it will get an extra push of velocity, and you will be able to go further without having to pack extra fuel on the trip. Okay, so I'm going to tell you a bit about another interesting maneuver that you can do in space, and it's called docking. Who here actually knows what docking is? 1, 2, 3, okay. Okay, quite a lot of people, that's good. Docking is actually when two spacecraft meet in space. So basically that's also what happens when astronauts go to the International Space Station. They need to actually meet up with the space station and dock to the ports of the space station to be able to enter inside. And you could think that this is a quite easy maneuver to do. It's just to like bring two objects closer to each other, but it's actually pretty difficult to do. And I'm going to explain you a bit how this works. So imagine that you have two satellites moving in the same direction. So they are both moving in that direction. Now, you want this second satellite to basically approach this one and to dock to it. And you have two options. You can basically tell the satellite to go forward, or you can tell the satellite to go backwards. Which one would you choose? Who would say going forward? Okay, who would say going backwards? Okay, some people. Actually, the right answer is backwards. And it's a bit curious, and it has to do with the velocities that I talked about in the different orbits, which is a bit counterintuitive. Because if you propel your satellite backwards, it will actually lose a bit of speed, right? And losing a bit of speed will make it go down to a lower orbit. And actually, once it's down in the lower orbit, it will be faster than the other satellite, right? Because it's in a closer orbit to Earth. And then it will move faster forward. And once it's pretty much close to the other satellite, you can actually, again, then put a force forward on the satellite so that it raises up the orbit again. And this way you have approached the other satellite to the first one. This is a very simplified version of how it actually works, but you can see that it becomes quite complex to maneuver two satellites in space. Okay, so to finish up a bit, I wanted to talk a bit about the space environment, because it can also be very curious and also quite dangerous, especially if you have astronauts in space, right? And I want to talk to you about temperature first. So basically, you see here, if you imagine that this is the Earth, the sun is quite hot, and it's not so far from Earth, actually. So if you have satellites in orbit, if they are on the side that points towards the sun, they can actually reach temperatures up to 120 degrees Celsius. And on the other side, if the satellite is pointing towards space, which is actually a very cold place, the temperatures can be up to minus 160 degrees Celsius. So you see that it's a bit difficult to get the right temperature, especially if you have people in space, because then you have to do a lot of shielding and a lot of heating, depending on where you are in space. The other thing that can actually kill you is radiation. And most of the radiation that we see close to Earth is actually coming from the sun. And basically the only thing that protects us from this radiation is the magnetic field of the Earth, which actually, it actually protects, you see there is this kind of shield, and this is because of the magnetic field of the Earth. So it actually deflects the solar winds and the solar radiation around Earth. And we're very lucky that we have a magnetic field, because otherwise we would probably not be able to live here on Earth. So you see that actually when you are in a close orbit to Earth, this doesn't affect so much, but actually when you go to a further orbit around Earth or even to other planets, this is actually a big concern. especially if we then in the future want to have astronauts on Mars. It will be a big concern to actually protect these astronauts from radiation. And another thing that I wanted to talk to you about is zero gravity. So zero gravity is what we call, well, the environment in which astronauts live, right? It's floating around in space and sometimes playing games with each other. And it seems like an environment where you basically can float around and do anything, right? And the curious thing about zero gravity is that people usually think that zero gravity means that you don't have any forces acting upon you. But this is not true. Actually, zero gravity, what we usually call zero gravity, means that you have only the gravitational force acting upon you. And if you remember the pictures that you saw in the beginning of the ball going around, actually what you see here is that if you are in an orbit and you have a certain velocity, there is no other force that acts upon you than the pull of gravity. And this is actually what makes you stay in the orbit, right? Because if there wasn't a gravity pulling on you, you would just go forward and you would float out into space. So it's a bit curious that we call it zero gravity, and usually scientists prefer microgravity than zero gravity. And there are actually ways that we can kind of replicate this here on Earth to do, for example, to do experiments, to see how we behave in zero gravity, to see some effects on the human body, etc. And we can do this in what we call zero-G flights. This is me. I did this 1 year ago, which was super cool. And basically, I'm going to explain you a bit, to finish up a bit, how these zero-gravity flights work. And the way it works is basically like this. So you have an airplane. It's a normal airplane. It's just been stripped of all the seats inside the airplane so that you don't crash into stuff. And it's been padded on the walls so that you don't hurt yourself. And what the pilots do is that they actually, they start with a pull-up. And here you can see that there is a hypergravity period where you experience a gravity of almost 2G when you pull up. And usually this angle is around 45 degrees. And this lasts for a bit less than 1 minute, basically. And then once you come to this point, what the pilots do is that they turn off the engine. And they are able to maneuver the plane so that only the gravity force affects the airplane. So basically they tilt the plane at an angle so that it counteracts the drag and all the other forces that are exerted on the plane. So that during this part of zero gravity, only the gravitational force is acting on you. So basically it's as if you were falling in free space. And this period lasts for around 20 to 30 seconds before you come crashing down on Earth and you actually have to pull out again. And then basically the pilots do another maneuver to pull out of this free fall. And again, you have this hypergravity period of almost 2 Gs. And then basically you repeat this, and you do this over and over again, around 30 times, so that you have time to do your experiments and to have time to basically get your work done. And to finish, I have here a small video of me in zero gravity. And I'm trying to do some gymnastics. It's not going very well. It's a lot harder than you think to do these things in zero gravity. I'm sure the astronauts have a lot of training. So this is around 20 seconds of zero gravity. And then in the end, boom, it stops. So with that, I want to thank you very much for the attention. And mind if you have any questions. I would be happy to answer them. Should I give this microphone or? Thanks.
So thanks for the amazing talk. If human space travel is to become ubiquitous, this might be a bit forward thinking, but imagine getting like a jumbo jet into space, lots of people. How do you counteract the rocket fuel problem? Because as we saw, if you add a pound of mass to the payload, you have to add like 9 or 10 pounds of fuel. And then you have to have more fuel to take that fuel out of orbit. Yeah. So how would you counteract that?
There are a couple of ideas to make rocketry more efficient. Some people have thought about using microwaves, for example, instead of fuel to propel the rocket, etc. But truth to be told, since we actually started with rocketry in the, what was it, 40s, 50s, it hasn't changed so much. We made it like a bit more efficient, but there hasn't been like a jump in efficiency. And I think that has to come to be able to like make it sustainable for people to go out in space. Right now, you could go up to, I don't know, 50 or 100 people, but you would have to build a super big rocket. But if you want to like actually have mass movement into space, I think it has to be like a change in efficiency, basically.
It has been recently in the news about reaction engines in the UK that is building the Skylon. I don't know the name of the engine. And what do you think about it? Is single stage to orbit viable with this kind of technology, or?
So I think it's difficult to say. I haven't read so much about it, so I'm not an expert on this area. I think it could be viable, but you have to make it much more efficient. And I don't have the numbers in my head how efficient these engines are. But for example, there are people doing air launches, and in that case, maybe you could actually have a single stage, but then you would have to carry the rockets basically with an airplane to an altitude where it makes sense to launch only one stage. There are also some companies trying to do balloon launches. So basically they go up with a balloon until a very high altitude and then they launch from there, which is also better because then you don't have to think so much about the drag. So they can have like different shapes of the rocket. They don't have to be very aerodynamic as they do on the, how do you say, land launches.
More questions?
Hi, thank you for the talk. And my question is regarding docking. Mm-hmm. And this is more of a human problem than anything else, because we see a lot of countries in space or doing space exploration, but there must be a standard docking station or something like that, correct? Otherwise, mm-hmm. It would be impossible for, let's say, a Russian space shuttle to dock on anything else. How does it work? Is it very complicated to get people agreeing on a standard, not only for docking, but for anything else?
So I think it's an interesting question to ask, because I think in space actually is one of the areas where most countries actually collaborate on these things. If you look at the International Space Station, it's like the biggest project that has been done by a lot of countries on Earth. And in that case, for example, you need to have a standard, right? Because there are the US shuttles that were docking, there are the Russians that are docking. So basically there you have to have a standard. And I think if we in the future have another space station, well, they already know more or less how to standardize it. So I think it's easier to do that.
Thank you.
So just a quick follow-up on that question.
like, yeah, space has always been like very international and collaboration. Do you see that changing with commercial endeavors into space? Because suddenly it's not only governments and everyone, and as we know, business is driven by money, not by, well, unless you're Elon Musk or something, but yeah. So what's your take on that?
Yeah, I think it will change quite a lot with the commercial space, especially if people build their own space stations like Boeing wants to do and like SpaceX probably also wants to do in the future. And you will, well, hopefully you will see also more space tourism and things like this. So it will change a bit, but I think that governments will always play a big role in it because there's a lot of things that are, for example, science that private companies will probably not put so much money in because it's not profitable in the end. So I think governments and collaboration between nations will always play a big role in the science of space. And we need the science to be able to explore further.
More questions? We still have time if you want to have a go. Okay, I guess you're free to go.
Thanks. So if you guys want, if you haven't passed by our booth yet, from the Valley Space booth, you can actually make our rocket challenge where you can build your own mini rockets. So if you want to try that, you can come by after.
Thank you.